Okay, so tonight we're going to be in 14.4. It's going to feel like something totally new for a second, but then we're going to come back to systems of equations. And so what we are going to talk about today are these mathematical entities called matrices. It's called a singular is a matrix, and several are called matrices. And essentially, a matrix is just a collection of numbers, a collection of objects, and you order those into a nice, it's almost like it's a table of numbers, only we don't draw the grid lines. And so we have rows and we have columns. Rows are horizontal, columns are vertical. And here I have how you write a general matrix. And so, A11, and in the case of this example down here at the bottom, A11 is the number 1. So the number 1 would go in its spot. And it's really, it's just mathy stuff, but it's saying it's the entry in row 1, column 1. And this one is the entry in row 1, column 2. And down here, this would be row 3, column 2. So we have a matrix, and we say the order of the matrix is the number of rows and the number of columns, where you would say it's m by n, where you have m rows and n columns. Okay, so we're going to just talk about rows and columns for a second. I have 4 example matrices here, and I want to know the order of them. So this first one, if you see, I can count 1, 2 rows by 1, 2 columns. So this is a 2 by 2 matrix. On the next matrix, I have 1, 2 rows again, but then if you look at the number of columns, there are 3 columns. So it's 2 rows and 3 columns. And why don't you go ahead and fill in the next 2. Okay, so where does this come into play with systems of linear equations? Well, what we do with a system of equations is we write them as augmented matrices. And the augment is just because of this equal sign here. That's where we augment it. But really, all that matters in a system of equations are the coefficients. Not the x, not the y, not the z, not the w in this case. Really just the coefficients of the numbers and the order in which they're given. Okay, so what we're going to do is we're going to take this system of equations and we're just going to say, well, this is really all that matters are these numbers. Okay, and so I have to put these in order here. We need to decide, let's go by this bottom row here. We're going to put the x's in the first column, the y's in the second, the z's in the third, and then we'll put the w's in the fourth column. And so if you look at the first equation, I have 2 x's, 3 w's, and negative 4 z's. There are no y's, so I'll put a 0 there. Okay, and then here's the augment part, and this is where the equal sign goes. And then we're going to put the constant term that we equal on the right, so that would be a 5. So what I've done is taken this very first equation, 2x plus 3w minus 4z equals 5, and I've written it as the first row of this matrix. And the first, so in the first column, I put the x's, second column y's, third column z's, fourth column w's, last column after that bar here, which is the augment part, I put the constant that it equals. Okay, so let's finish this up. In the second equation, I have negative 1x minus y minus 15z plus 1w equals 1. And in my third equation, 12x, 3y, negative 6w, looks like I have 0 z's, and that equals 9. And then in my last column, 1, 1, 1, 1, or last equation, I had 1x, 1y, 1z, 1w, and that equals 20. And so here I have taken this whole system, and I've just pretty much dropped the x's, y's, z's, and w's. And it looks like all that matters is those numbers. Okay? All right. So now let's do the reverse. Here I have a matrix, an augmented matrix, and I want to write this as a system of equations. And so use variables x, y, z, and w. I am guessing that we will not have any w's on this since we only have 3 rows or 3 columns. So the first equation will be x plus 3y, there's no z, equals 8. And then in the second row, I get negative 2x plus 3y plus 6z equals 5. And there you go. This is the system of equations that this matrix represents. Okay, so now we're going to go back to what we just did. We want to solve systems of equations. And so we're going to do this Gaussian elimination, the Gauss elimination, and we want to put the system of equations in row echelon form, in reduced row echelon form, or row echelon form. And so you're going to do the same sorts of operations that you could have done on the systems of equations. You can switch around the equations, which one's first, which one's second. You can multiply anything by a number, and you can add two rows together if you'd like. Okay, so that's these are what we can do. Now, to be in the correct form in which you can back substitute easily, like we did before, you want to have these three criteria. So if you have any all zeros, we stick those at the bottom. Then after that, this is just, I don't like to do this. I think it's easier to solve without doing this, but this is technically what you need to be in row echelon form. You need the first entry in the row to be 1. So you go row by row. The bottom row, or if you have any 0 rows, they have to go in the bottom. And then as you read across the row, the first number you should read should be 1. And then the other thing that happens is you have to have this sort of diagonal where the ones get more to the right the further you go. Now 1 can be directly below, but it can't be to the left. Okay, so for example, in this first matrix, if you look, this first row is good. The first number I saw was a 1, okay? Then the second row, it looks like I have a 0 here, which is great because there's a 1 above it. There are no ones left of this top one. Okay, but this one's no good because of this 2 here. The first number I'm supposed to see is supposed to be a 1. And so this is not in reduced row form. It's not in row echelon form. The second one is, because the first number I see here is 1, and the first number here I see is 1, and this one is not to the left of that one. It's lower and to the right. And finally, this matrix is also in row echelon form, in reduced echelon form, because there are never any 0s or 1s left of the original ones. It's kind of a trite example. Okay, so you want to see the first number has to be a 1, okay? And then any other ones, so I couldn't, this is my first row, and I automatically do this, but I couldn't have had 0, 1, 2, 4, 1, 0, 1, 3, because this row is this one is to the left of that one. You would have to switch these rows, and then you would be in reduced row echelon form. And so that's the goal. We're going to take a system of equations, we're going to put it into an augmented matrix, and then we're going to do row reduction operations until we get reduced row echelon or row echelon form, and then we can back substitute. All right, so let me show you how this works. First of all, I'm going to write this as a matrix. 1, -2, 3, 9, -1, 3, 0, -4, 2, -5, 5, 17. Okay, so the first thing I'm going to do is just like what we did when we had an entire equation. My first goal is to make this entry and this entry both zeros. I need to eliminate the x coefficients, the x terms. So in order to, and I'm not going to change my first row, it's okay. So I'm going to keep it 1, -2, 3, 9. Then on the second row, I'm going to take the first row plus the second row, and that is my new second row, because I already have 1 and -1. If I just add them together, I'll get 0. If I add -2 and 3, I get 1. If I add 3 and 0, I get 3. And 9 plus -4 is 5. Okay, so now I have to do some multiplying to get rid of the 2 here on the third row. I'm going to take -2 times the first row and add the third row, and that's my new third row. Okay, so that will get me 0 here, but -2, so if I multiply by -2, then these are the numbers of my first that I'm adding to my third row to get my new third row. So this will give me -1, -1, and -1. That's kind of funny. All right, now I'm still not done yet because I need to take this number here and I want to make it into a 0 if possible. So I'm not going to change my first two rows. I'm going to leave those the way they are. So I'm coming over here now. 1, -2, 3, 9, 0, 1, 3, 5. Not changing those. But in order to eliminate this, again, it's easy. I just need to take row 2 and row 3 and add them together. And that's my new row 3. I have to use this number here to make this number a 0, okay? That's just if you have to stay within the column in order to change this column, because otherwise you would, if I use my first row to do it, then I would lose this 0 here, and I don't want to lose that 0. Okay, so I'm using row 2 to eliminate the 0 in the second column of row 3. And so when I add these two equations together, I get 0, 0, 2, 4. Now this is not quite yet in row echelon form because the first number in the third row is a 2, but it's supposed to be a 1. And so in order to fix that, I just need to take the third row and divide it by 2. And that's my new third row. And that's an okay operation to do. So we get 1, -2, 3, 9, 0, 1, 0, 1, 3, 5, and 0, 0, 1, 2. Okay, and then at this point we are in reduced in row echelon form, and you can read from the bottom here and back substitute just like we did with our systems of equations, because the bottom equation tells me that that's a z, that 1z equals 2. And then if you look at the second row, that tells me that 0x's plus 1y plus 3z equals 5, but I know that z is 2. So I'm going to replace that z with 2. So y plus 6 is 5, and so y is -1. And then finally, I can take my top equation here, and I get x minus 2y, so that's plus 2, plus 3z plus 6 equals 9. And so x plus 8 is 9, and so x equals 1. And so now I have the solution, and I didn't have to deal with x's and y's and z's the whole time. So 1, -1, 2 is my answer. Okay, you can further see, I kept using the word reduced row echelon, but you can do further reduced row echelon, and in this one you make zeros in the top as well. So the perfect reduced row echelon form of a 3x3 matrix is this one right here. And in this one it would be perfect, because if you looked and you got all ones in the diagonal and zeros everywhere else, then you can just read z equals 3, y equals 2, x equals 1, and it's a lovely thing to do. And so what we need to do, and this is in reduced row echelon form, because the first number you see is 1, and then above and below that 1 are zeros. Okay, now this is and notice the third row is all zeros, so the all zero row goes on the bottom. This is also in reduced row echelon form, and this is a perfect 2x2 reduced row echelon form, where you have a nice square matrix and no rows of zeros. It's perfect. The third one here, which is dotted around it, you cannot, if this is not in reduced row echelon form, you would need to switch these two rows, and then it would be, because the zeros still need to be on the bottom. Okay, and so this is called Gauss-Jordan elimination, and I'm going to show you how to do this. This is the best process of elimination, and this is what I'm going to use all along. In this process, you're going to use the first row to eliminate the x's, just like we've done before, the bottom two x's. So you're going to use this number here to make these zeros once we get matrices. Then you're going to use the second row, or the second equation, to eliminate the top and bottom y's, right? Just like they are in this one. And you have to use the second row to do that. So you're going to use this number to make those two zeros. And this is going to, each of one of these things takes one step. Well, at least one step. And then you use the third row to eliminate the top two z's. Okay, so you're going to use this, not that one, this number here to make these into zeros. Okay, by the time we get to this step, this one won't be a zero. That one will not be a zero at that point. And you're going to do it in this order. Okay, and so what I have done here is I have written my system of equations as an augmented matrix. We're going to do just what I said in the same order we're going to do that I said to do it in. So it's just like reducing the systems of equations, but we're using a matrix. So to eliminate this -1 and make it into a 0, I'm going to take row 1 plus row 2, and that's my new row 2. And I'm not changing row 1 any. So every time we do an operation, we're not changing one row, but we are changing the other two. So when I add these together, I get 0, 1, 3, 5. Then to eliminate the 2 in the bottom row, I need to take row 1, 2 row 1, minus row 3, and that's my new row 3. So 2 row 1 minus row 3. So it's going to be 0, -9. That would be 1. And 18 minus 17 is 1. Okay, so I've gotten my zeros underneath the 1 in the first column. Now I'm going to work on the second column. I'm going to use row 2, this row. That's the row I'm not going to change. And then I'm going to make these two numbers into zeros. That's the goal in this next step. So I'm going to come over here, and I'm going to rewrite my second row. Not going to change it. I'm going to use it to change the other two. Okay, so it looks like to get a 0 in the first row here, I'm going to take 2 times row 2 and add row 1, and that's my new row 1. And so this is one thing that's different in the Gauss-Jordan elimination. We want to get zeros above and below the leading ones. So 2 times row 2 plus row 1 is row 1, and it happens everywhere. So 2 times 0 plus 1 is 1. 2 times 1 plus -2 is 0. 2 times 3 plus 3 is 9. And 2 times 5 plus 9 is 19. Okay, then I'm going to, in order to get a 0 in the third row here, I'm going to take 9 times row 2 and add row 3, and this is my new row 3. So 2 times 0 plus 0 is still 0. Or sorry, 9 times 0 plus 0 is still 0. 9 times 1 plus -9 is 0. 9 times 3 minus 1 is 26. 9 times 5 minus, wait, I'm adding. This should have been 28. 9 times 5 plus 1 is 46. Okay, now, hold on, I have found a mistake. This -9 is not supposed to be a -9. I added wrong when I did this operation here. So I took 2 times row 1, and I added row 3, and so I subtracted row 3. So I should have gotten -4 plus 5, which is +1 there. Okay, and that doesn't change anything else in this step other than this bottom row. And I'm not going to perform the same operation. So I'm fixing that now. So what I should do is I should take row 2 minus row 3, and that's my new row 3. So I get 0, 0, 2, 4. Row 2 minus row 3, that's my new row 3. Okay, this looks prettier. Now we're almost done. In the last step, we are going to eliminate, we're going to use row 3 to eliminate the top 2. So I'm going to not change my row 3. Okay, so before I not change my row 3, notice this 2 and this 4, okay? Let me the 2 and the 4, I can divide that by 2 and get 1, 2, and that will be easier to work with. So I'm going to sort of do a sub step 2 there, and I make that 0, or I'm going to divide by 2, and I get 0, 0, 1, 2. Some people do this as its own step. Some people just see it and then erase it and then write in the 1, 2. Okay, and that's going to be way easier to work with. So now I'm going to take this 1 here, and I'm going to make these 2 zeros. And then I'll be perfect in reduced row echelon form, and I perform Gauss-Jordan elimination. So I'm going to take I got to make this 3 into a 0, so I'm going to take -3 row 3 and add row 2, and that's my new row 2. So -3 times the bottom plus the middle is the new middle. So that's 0, 1, 0, and -3 times 2 is -6, plus 5 is -1. And now for the top step, I'm going to take -9 times row 3 and add row 1, and that's my new row 1, because that will make this 9 into a 0. So I didn't change the 1, 0, because I take -9 times row 3 plus row 1. So 0 plus 1, and 0 plus 0. And now -9 plus 9 is 0. And now -18 plus 9 is 1. And so I'm in perfect reduced row echelon form, and you can perfectly see the solution to the equation. This is the z, the y, and the x. And so we get the solution 1, -1, 2. And we're all done. It's so much easier with matrices. Okay, so I'm going to do this one last example. This is one where I have 4 equations and 2 unknowns, and the answers are going to be in terms of, they're going to be infinitely many solutions. So I'm going to take this and make an augmented matrix. And there's not a whole lot that you can do here to make this to do the Gauss-Jordan elimination. We really just need to make this bottom one here a 0. And unfortunately, this is not going to be pretty. So I'm going to take 3 row 1 minus 4 row 2, and that's my new row 2. All right, so I'm not changing the 4, 12, -7, -20, 22. So now I get a 0 here because I get 12 minus 12. Here I'm going to get 3 times 12, 36, minus 4 times 9, 36. So that's a 0. I get 36 minus 36. 3 times -7 is -35, plus 20 is -15. -60 plus 4 times 28, 112. So I get -60 plus 112, so that's 62. Equals 3 times 22 minus 4 times 30. So it's -120. 3 times 22 is 66. 66 minus 120 is -54. Okay, and so I've done all of the eliminating I can do. I don't have leading ones, but I don't want fractions, so I'm not going to bother making leading ones. I'm going to go back to, I'm going to look at this bottom equation here. And we have that -15z plus 62w equals -54. And so all I can do to solve is I can say let w be a and let z be b. Okay, then what happens, oh no, let me not do that. Let's let w be a. And then I can solve for z in terms of w. So -15z plus 62a equals -54. And so -15z equals -54 plus 62a. And so z is 62a minus 54 over -15. And now I can substitute that into the top equation, and I think I have to let y be b, and then I can solve for x in terms of a and b. And this is turning into a little bit of a nightmare. So let's pause this and let's work on this when we get to